Hi everyone, today we're going to look at a refraction scenario and work this one out. I've got a little drawing here and we'll go through the question and figure out what we have. So, you are underwater with a waterproof flashlight and you shine it upwards such that it makes an angle of incidence of 45 degrees. Determine the angle of refraction of the light as it leaves the water and enters air. B, what is the greatest angle you can shine the light at and still have refraction? And C, what would happen if you exceeded the angle in part A? So we'll go through the question. We'll highlight like we've been doing. So the angle of incidence is 45 degrees. And we want to find the angle of refraction as it goes from water into air. And then we want to find the greatest angle. So that would probably tell me critical angle. In part C, what would happen if you exceeded the angle in part B? So let's draw a few things. I'm going to pick draw my line one here. I'll do this. So remember, we have our light is going to come up from the flashlight and hit the surface. Remember, we always have a normal line here, and then the light is going to go there. And if you remember, if it goes from water to air, it's going from more dense to less dense. So it's going to refract down this way. So let's write down what we have. We know we have the angle of incidence. The little I means incidence. 45 degrees. We're looking for the angle of refraction. We know we have water, so water is our incident angle, so it's coming from this side. So this is going to be our NI, and this will be our NR. So our NI is water, and you can look in your tables, but maybe you're used to this one right now. 1.333, and that is water. And we also have the refracted material, which is air. And air is 1.00029. It's pretty close to 1. It doesn't make a whole lot of difference, but it can change your angle by a couple decimal places. It's not a big deal. So this is air. So this is the refraction question. For refraction, we've been using the same formula all along, so let's pick this one out. If you don't remember it, look at your formula page. It is Ni sine theta I equals NR sine theta R. I'm going to put my numbers in now. So I've got water, 1.333 sine of 45 degrees equals air, which is 1.00029 sine of the angle of refraction. That's a R. So this angle right here, that is our theta I. That's 45 degrees. And we want to know that angle. Oops, sorry. This angle right here. So this angle should be bigger than 45. So let's see if this works out. So 1.33 times the sine of 45, should be able to put that all in your calculator, and I get 0.9426 equals 1.00029 sine of theta R. I'm going to divide that, and I'll get nearly the same number. Oh, sorry. This number, looking at my sheet, this number is 1.333 sine of 45 divided by 1.29. So that whole thing is sine of theta R. Sorry about that. And of course, to find the answer to that, I have to do the inverse sine of that number. So the inverse sine of 0.9426 is going to equal the angle of refraction. And the angle of refraction should be 70.49 degrees. That is my angle of refraction in the current scenario. Part B says, what is the greatest angle you can shine the light at and still have refraction? So what I'm going to do is I'm going to take this guy here so I can move it. I'm going to take him and I'm going to turn him a little bit. And so he's going to make a greater angle. So now, my line here, the angle is going to change and it's going to become greater. And let's just change the color. That's so we know it's a new scenario. So that is, let's make it a red line. So now At the greatest angle, if you recall, the greatest angle is the critical angle. At the critical angle, I'm going to have refraction. Let's change color of that so it matches. So at refraction, so when I have refraction, remember theta r equals 90 degrees of the critical angle. So it's going to be the same formula again. Sine theta I, Ni sine theta I equals Nr sine theta R. We're going from water, 1.333, and we don't know the angle of incidence this time. I'm trying to find that. Equals air, 1.00029. Sine of, put the 90 below because I'm a little tight for space. Sine of 90, the sine of 90, if you recall, is 1. So I'm going to get sine of theta equals, so this is going to be 1.00029 times the sine of 90, which is 1, divided by the 1.333, and I should get a number that is 0.7504 is what I worked it out to. So theta I is equal to the inverse sine. Remember, if we're looking for the angle, we have to do the inverse sine. 0.7504. And I do the math of that. Put that in your calculator, and I have 48.60 degrees. So when you shined it at 45, or when you shined it at 45, you get an angle of 70. If I shine it at 48.6, suddenly it's at an angle of 90, and it goes right across the surface. That's my critical angle. And part C says, what would happen if you exceeded the angle in part B? You've exceeded the angle in part B, so you've exceeded the critical angle. So that you would then have, if you've exceeded it, you would have total internal reflection. So I'm just going to type that out here. Change the font size to 16. The angle of refraction is 70.49 degrees. And I'll get it. So the angle of refraction is 70.49 degrees, and the critical angle is 48.6 degrees. Anything greater than that angle will result in internal reflection. As always, if you have any questions, send me an email or pop in and see me, and hopefully this helps a little bit. Thanks.